Hello again and welcome to another physics video. Today we will be continuing the topic of lenses, and this time we will be focusing on more general rules, nice tricks that will help you in your exams, and filling out the corners of this topic. These tricks are very useful, so mostly just faster ways to solve things, which is what a lot of physics is about, finding smarter ways rather than difficult, long-winded ways. Alright, so just to remind you, last time in our first lenses video, we had this general setup of a lens here and an object here, and light comes off the object and is refracted by the lens, and the light bends and forms an image here. Important thing to note, which I didn't mention in the last video because it's much more relevant to this one, is that this is specifically called a real image. I'll show you when it is not called a real image in just a moment. Now, if you need reminding, go and watch the last video, but I also introduced focal lengths. The definition of focal length is when an object is placed at infinity and it is where the image is formed, which will be over here. So just imagine this setup reverse, but you can watch the last video if you need just an extra bit of explanation on that. Alright, and we also showed what happens when the object is placed at the focal length. So these different rules that we want to explore is what quick things do you know about the image just from where the object is placed. And the first one is what happens if the object is placed at the same length as the focal length. Next, we think, okay, what if we put the image just a bit closer? Well, as you can see, the rays have done something very interesting here. They have diverged. Now, that's what this is now, a diverging image. So, if you look at the trend, this is definitely greater than the focal length, this distance here, and you get a nice real image at a point, some point. And if you place it even closer, you will get no image formed because the rays never meet. And if you place it even closer, well, there's definitely no image formed over here. However, something you need to know is that the rays do still meet, just not this way. If you follow them back over here, the little messy line, very rough, you will see they do actually meet at somewhere around here. And right here is called, well, this is the image distance, but more specifically, this right here is called a virtual image. Now, remember, real image, virtual image. Now, if you remember in the last video, the object's distance was always negative and the image distance was always positive. However, in this case, when it's a virtual image, you can see that the image is on the same side as the object, which means that the image distance is always going to be negative. So that's just something you need to remember, that in this case, when it's on the same side, the image distance is going to be negative. Alright, so there aren't too many rules to remember. There's one more rather important one, well, useful one I should say, could come up, that if the object distance is placed at twice the focal length, as we can see, 2f, then the image distance is actually going to be the same as the object distance, which is rather useful. I've just proved that to you using our lens equation. If you remember from last time, 1 over v equals 1 over u plus 1 over f. So in this case, if we just imagine that the object distance, sub that in, is 2f, so 1 over 2f, well that should be minus 2f, just to be clear, 1 over minus 2f, plus 1 over f. Now if we just find a common denominator, or at least positive common denominator, this is going to become 2 over 2f, so you've got 2 over 2f minus 1 over 2f, which is 1 over 2f. So what we know from this, we've got 1 over v equals 1 over 2f. Therefore, turn upside down, the reciprocal is v equals 2f. Now would you look at that? So v is definitely equal to 2f, which, as we stated over here, that u equals 2f. So there we are. Image distance is equal to object distance when object is placed at 2f. Alright, so as we're saying, this is more about rules, and this time, rather than just looking at a single point, obviously most objects are not from a single point, so just to wrap your head around it, here's a nice little smiley face, and if we look, just the same things is the light rays are coming from individual points, so the same rules apply, and the image is formed here for that point, and the image is formed here for that point, but overall the image is formed over here for the entire face. And as you can see, the rules applied are that the image is flipped. Nice easy rule. If you're working with something that isn't a point, you can always remember that. The image is always flipped. That might just be a multiple choice question, or just something you need to list about what happens to an image when it goes through a lens, or this kind of lens at least. But more importantly, the image is magnified. I'm sure you're familiar with the concept of magnification in real life, but it is very important. So it's very simple, just by a simple equation that magnification equals image distance over object distance. So that's m equals v over u. So it's just how big the image is compared to the object. So image over object. Obviously, big might sound a bit strange because I'm talking about how far it is from the lens, but it will come to the same thing. There is another way to solve this, which is something we haven't quite looked at yet. In all my examples, the object has been sort of placed on this axis here. Just to make it simpler though, we can see that if this is all we have, we can use the object height and the image height. And in this case, it will be the exact same thing, image height over object height equal magnification. So just anything to do with the image over anything to do with the object is what you will get. If we want to just take a look at this really quick, and we can have a look at how you actually can figure out where images are formed in this case, or well, in any case really. So all you need to do is have a look at the rules we know so far. So first thing you always do is just get a line from the object and draw it straight through the center of the lens, and it won't be refracted at all. Everything cancels out, and just draw a line there. And then what you need to do, notice this is coming in perpendicular to our lens axis, and that's very similar to when we place our objects at infinite distance away. As you can see, you can imagine that you have your parallel rays coming in here, and then what happens? The image is formed at the focal point. So that would be here, our focal point. So all you really need are these two lines, because you'll draw your perpendicular line to the image, to the lens axis, and then your line straight through the center, and then all you need to do is have them meet, because you know that this will go through the focal point and they'll meet here. That's very useful. You can just replay that a couple of times if you just want to grasp it a bit better. Now, just for completion, I'll do a quick example. We can use either object height or image distance and object distance, but we'll just solve magnification, and we'll use this one here because we're less familiar with it, just so we get more comfortable. So let's say the object height is 1 meter. So this is 1 meter, and let's say this is half a meter. so 0.5 meters. So all we need to do, very, very simple. I'm sure some of you can just look at this and know that it's magnification. It's been, decreased, so it's been halved. It's been decreased by a factor of 2. So you've got image height is 0.5 over object height, which is 1, equals, disappeared, 0.5. That's magnification. And there we have it. Very easy. Nothing too complicated here, just little rules to remember, tips and tricks. With practice, you'll come to know these very easily. It won't take too long. Okay, well, I hope you enjoyed and hope you learned, and I'll see you all next time. Thank you.